In section 1-7, we're going to be looking at linear inequalities as well as absolute value inequalities. So the first one, linear inequalities, you need to remember when you take an inequality, which is either greater than or equal to, less than or equal to, strictly greater than, or less than and strictly greater than, when you divide by a negative when you're dealing with inequalities, the inequality sign will flip directions. So in these next three examples, I'm going to ask you to solve each inequality and then graph the solution on a number line. So here's the first one. So what you do when you're solving an inequality is you're going to treat it as though it was an equal sign. The only difference is that if you divide by a negative or multiply by a negative, you have to switch the sign. So the first thing I'm going to go ahead and do is subtract the 7x over. And I end up getting 9 is greater than or equal to 3x minus 12. And then go ahead and add the 12 to the other side. And you end up getting 21 is greater than or equal to 3x. And then just to solve it as though it was an equal. I divide by 3. This cancels and I get x is less than or equal to 7. So here's my solution. So when you're asked to graph it, you would go ahead and put your number line. Let's say this is 0, 1, 2, 3, 4, 5, 6, and 7. And because it's greater than or less than or equal to, you're going to have a closed dot on 7. And these are all the x values that are less than or equal to 7, so you shade that way. And that would be your solution. In this next example, you're asked to solve where 3x minus 3 is greater than negative 12 and where 3x minus 3 is less than 15. So what you're going to do is you're going to solve it as though you kind of have two equal signs, if you will. So I'm going to go ahead and add 3 to not only the right side, but also the left side to get it to cancel. So when I go ahead and simplify this, I end up getting negative 9 is less than 3x, which is less than 18. And then to solve for x, to get x in the middle of the inequality, you divide everything by 3. So you're going to take everything and divide it by 3. So you get negative 3 is less than x, which is less than 6. So your solution would be x values that are bigger than negative 3 but less than 6. So you make your number line. Let's say this is 0. Here's 1, 2, 3, 4, 5, 6. And here's negative 3 right here. It can't equal, x can't equal negative 3 or 6. So I have open circles there. And since these are all x values that are bigger than negative 3, that's this way, but less than 6, I'm going to shade right in the middle. And it's not equal to either one, so they're open dots. For the last type of linear inequality that you're going to see, you have the two inequalities, and you can have x values, negative 2 times x plus 7 less than 3, or you can have 3x plus 5 is less than 2, and you want to find all the solutions for either those or that. So it's like two problems in one. So what you're going to go ahead and do is solve this inequality right here. So I'm going to go ahead and add 7 to both sides. Or not add 7, but subtract 7. Let's try that again. And what I'll end up getting is negative 2x, this cancels, is less than negative 4. Now here's where you have to be careful. See how I'm dividing by a negative 2? Whenever that happens, this is now going to become x is greater than positive 2. So far I have x values that are bigger than or equal to 2, or I have to now solve this one. So I'm going to go ahead and subtract 5 from both sides. And when I do that, I get 3x, this cancels, is less than negative 3. And I'm dividing by a positive 3, so I don't have to worry about switching the signs. I get x is greater than, just kidding, less than, because the sign doesn't actually switch, negative 1. So my solutions would be all x values that are greater than 2 or less than negative 1. So when you plot those on a number line, here's 0, here's negative 1, and here's positive 2. Now notice how these are not equal to in each case, so that means they're both going to be open circles. So x values that are less than negative 1 would be this direction, and x values that are greater than 2 are going to be this direction. and so you have your two ends of the graph that look like that. We're going to be solving absolute value equations, and this is the equation that we're going to be solving. To solve the absolute value of ax plus b equals c, you're going to solve the equation ax plus b equals c. So you're going to take what's inside the absolute value and just set it equal to what c is. But remember, the absolute value of 7 also equals the absolute value of negative 7, and it always comes out positive. So you don't know if the inside is positive or negative. The result will always come out positive. So you're going to be solving this ax plus b equals c, and you're going to go ahead and solve ax plus b is equal to negative c, because again, you don't know if the inside is positive or negative because the output is always positive. So we're going to go ahead and solve 4x minus 11, the absolute value of that equals 25. So the first thing I'm going to go ahead and do is set inside the absolute value equal to 25, and then I also have to solve another equation where the inside of the absolute value could also be a negative 25, because again, both of them can be, the absolute value of each of those are always positive. So then I just go ahead and solve. So I'm going to go ahead and add 11 on this one. So when I go ahead and do that, I get 4x is equal to 36. So when I divide both sides by 4, I get 36 fourths, which is also equal to, it's equal to 9. And then I'm going to go ahead and do the other one. So I'm going to go ahead and add 11 to both sides. So when I go ahead and do that, I get 4x is equal to negative 14. So when I go ahead and divide both sides by 4, I get negative 14 fourths, or negative 7 halves. So the two things I can actually have are x is equal to 9 and negative 7 halves. And again, you can always check your equation to see if it's right by just plugging it in to the original equation. So I can go ahead and plug it into there to do the check. Is the absolute value of 4 times 9 minus 11 equal to 25? And I get 36 minus 11, yep, it's 25. And then plugging this one into there, I get 4 times negative 7 halves minus 11. I want to know if that, the absolute value of that, is equal to 25 as well. So when I have that, it also checks out. So get in the habit of checking your answers to make sure they work. The next thing we're going to be moving on to is solving absolute value inequalities. And you remember absolute values, those always make things positive. So I'm going to start off with kind of a general example, and then I'll give you the formulas. So let's say I had you solve the absolute value of x is greater than 3. And I told you to tell me all the x values that worked for. So you would say, oh, 4 works if I were to plug it in, because absolute value 4 is greater than 3. 5 would work, 6 would work, and so on. The other values that would work would be negative 4, because negative becomes positive, negative 5, negative 6, and so on. Putting these on a number line, I'll put negative 3 and 3. What I would have is all values, since I put negative 3 and 3 because of that, I would have all values that are bigger than 3 and less than negative 3. So when it's great or, you end up getting an or inequality solution, because those values work when you throw in an absolute value. So here's what the theorem is. So the inequality, the absolute value of ax plus b is greater than c, and this also works if it's greater than or equal to c, is equivalent to solving this right here. You're going to take basically the ax plus b, you're going to take the same thing that you have here, you're just going to take away the absolute value signs. You're going to solve what you have. If it's great or, notice how I'm emphasizing or, you're going to be solving an or linear inequality. So you're going to go ahead and solve ax plus b is greater than c, and then all you do is you solve ax plus b and you flip the sign and make c negative, and you're going to solve the two linear inequalities and you will get solutions that look very similar to that. This also works, so if this was greater than or equal to, then this would be greater than or equal to here, and if it was less than or equal to, this would be less than or equal to there. So just keep it in mind. It's all for the ones when you're solving ax plus b, the absolute value is great or than c. You're going to use an or conjunction right there, or disjunction. Well, what if the absolute value isn't greater? It's actually less than. And I'm going to give you a simple case of this. What about if I had the absolute value of x is less than 3? If you were asked to just find some values that worked, you'd say, all right, a value that would be less than 3 would be 2, 1, 0. You could plug in -1 as well, -2, and then that would work. So it's all the values between, if you were to put them on a number line, -3 and +3. These would be all the ones that would work, and it would be an open circle because it wouldn't equal to 3. So here's what it looks like for the theorem if you have a less than absolute value inequality. So the inequality absolute value of ax plus b is less than c, and again this can be less than or equal to. It'll just be less than or equal to in each of the formulas, or greater than or equal to in that case, is equivalent to solving. Now you're going to go ahead and copy down without the inequality, or without the absolute value signs, the same thing. You're going to solve the exact same thing. But when it's less than, you're going to solve an and inequality. So then all you're going to do is copy the same thing down, switch the sign, and make it negative, just like you did before. So if it was great or, so if this was greater, it'd be an or that you'd be solving. If it's less than, it's going to be an and that you're solving. All right, so we have a linear inequality, the absolute value of it equaling or less than or equal to 21. So notice how it is an absolute value, and it's less than. So because it's less than and it's an absolute value sign, you're going to go ahead and solve 4x minus 9 is less than or equal to 21, and then you have to figure out, is it going to be an and or an or in between the next one you're going to solve. Since it's less than, it's going to be and. So then now what you're going to do is you're going to take that 4x minus 9, and then you're going to switch the sign and make it negative. So it'll be now negative 21. And those are the two inequalities that you're going to solve. So I'm going to add 9 to both sides. And I end up getting 4x, this cancels, is less than or equal to 30. And then I'm going to divide both sides by 4. And I end up getting x is less than or equal to 7.5. Now, I'm only halfway done because now I have to solve the second one. So when I do that, I'm going to add 9, and this is greater than or equal to, well, I don't actually need that. I'm going to go ahead and do plus 9 here. And I get 4x, this ends up canceling, is greater than or equal to negative 12. And now I'm going to divide by 4, and I get x is greater than or equal to negative 3. Now the big thing that you want to keep in mind is if you can write this as one inequality, I want you to. So how you can check it is you go ahead and put this on a graph, and they're going to ask you to graph this in the homework. Here's 0, here's negative 3, and here's 7.5. 1, 2, 3, 4, 5, 6, 7, 8. Let's say that's 8. You have x is less than or equal to 7.5, so you're going to go this way when you shade, and x is greater than or equal to negative 3, you're going to go this way. So you know to shade in between. So basically, if you were to write this more in a condensed form, and any time it is an and, I will warn you right now, it can be written more concisely. These are all the x values that are between negative 3. So x is bigger than or equal to negative 3, but less than or equal to 7.5. So whenever it is an and, it can be condensed, and I want you to put it into one single inequality, and you can look at the graph to help you write it. Alright, so the last example, we have, again, an absolute value, so we're going to have to worry about if it's and or, and notice that it's great or, so you're going to have great or the or in between, and you're going to copy down the two things that you're going to solve. So you're going to copy down the original inequality. It's negative 3x plus 10 is greater than 7. Then you're going to put the words or in between because it's great or, and then you're going to solve the same exact thing but flip the sign. So I'll still have 3x plus 10, but now I'm going to flip the inequality and then make this negative. And then now I'm going to solve each. So I am going to subtract 10, When I do that, I get negative 3x is greater than negative 3. When I divide by a negative, I'm not going to forget to change the sign. So I'm going to get x is now less than positive 1. Or, now I'm going to get my second solution. I'm going to subtract 10 and I'm going to get negative 17 over on this side. And then I'm going to divide by negative 3. And again, don't forget to switch the side or the sign so you get 17 thirds, which is approximately like 5.7. So putting these on a number line, so here's your solution. You have x is bigger than 1, so let's say this is 0, that's 1, 2, 3, 4, 5, 6. And because it's not equal to, they're going to be open dots. So x is less than 1, and x is bigger than 5.7, which is about right there, let's just say. It's bigger than that. So because they're shaded in opposite directions, these cannot be condensed, and that's how you're going to write it. Ors stay ors. The ands are condensed like I did before, and that would be your graph. Okay, so that's linear and absolute value inequalities. That's a wrap. I'll see you guys tomorrow.